This is Brandon Tran, and this is my Lab 4 circuit, an inverting amplifier. We made it using a 1K resistor and a 12K resistor. We chose these values so that we get a gain of 12. So this is a screenshot of the output waveform at 1 kilohertz. So we found the slew rate by seeing the time it takes to turn back into a square wave. And this is done by finding the change in the y-axis or the change in voltage and putting that over the change in the x-axis or the change in time. When we did that, we got a slew rate of 0.032 volts per microsecond. After that, we also found it for the for the same signal at 10 kilohertz frequency, and we got 0.165 volts per microsecond. This is the sine output for the inverting amplifier. To verify that the gain was correct, we found the peak-to-peak voltage of the input, which was 192.8 millivolts, and the peak-to-peak voltage of the output, which was negative 2.196 volts, and we divided that by the input peak-to-peak voltage, and we got a negative 11.39, which is pretty close to 12, which was our the gain we were supposed to have. So this is a circuit which is a sum of 1, and the point of it is it has a high input impedance because the signal is directly applied to the positive terminal. This is the waveforms of it. As you can see, the two waveforms look very similar since the gain is. So this is the differential op amp. So it's a combination of an inverting and non-inverting amplifier. So it amplifies the difference between two input voltages. We chose to use two 1K resistors and two 10K resistors, so we get a gain of 10. We found common mode gain by connecting both input voltages, so having them from the same source. So this is the gain of my differential op amp. They intersect here, and this shows the phase of it. The magnitude can be found from this graph, and all of this is a function of frequency.